render in another way too. It's called line of sight measurement. So I'm going to explain how this line of sight measurement can be used for that instead of the distance rate. So the range between satellites or this, if we have the position of this of the position vector of satellite 1 and 2, the norm of this position vector of this satellite will be the distance, or in other words, R2. Let me write vectors so we know that these are vectors, R1. So the position vector of satellite 1, R2 is position vector of satellite 2. So the norm of this difference between the position vectors give you the distance between satellites. That's pretty clear. But what we need actually is the speed of the change or range rate. What can we do with that? So that's simple. This the derivative of this norm with respect to time. So if I take this derivative, the result will be the derivative, the difference between the derivative of this is vector 1, 2 over r. If you take the derivative of the absolute value, normally you can come to that. And this one is actually derivative vector, velocity vector of the second satellite and velocity vector of the first satellite. So then we have, if I take another derivative, the second order derivative, I come to this. The second order derivative with respect to time is called acceleration. So it will be dt derivative 1, 2 E LOS. What is E or LOS? It is called a unit vector pointing from satellite 1 to 2, or line of sight unit vector. What was that? If you remember, the equation was that the difference between the satellite divided by the distance. So this is the unit vector according to mathematics, unit vector. Now I take the derivative of this unit vector multiplied by this difference of the velocities, this equation, and come to this. So derivative of the first one multiplied by the second one plus the derivative of the second one multiplied to the first one. So it is dot means the derivative with respect to time, as you know. If I simplify this further, the first term is okay, keep it. And now if I take the derivative of that relation, what was that? ELOS delta R12 divided by rho. If I take the second derivative with respect to time, I come to this formula. The derivative of the minus the derivative and rho bar. And this one is the acceleration vector of the second satellite minus the acceleration vector of the first satellite. So what is that? this one, this acceleration vector is actually the gradient of the potential difference between satellites. It means gradient of V2 minus V1. So we find it. Here we have rho bar, and we have acceleration vector. We can connect it to, which is connected to the potential, and we have another measure quantity. So therefore, I keep this term on one side and the other one. And then after rearranging this, I come to this equation. So it will be rho acceleration. I should be bar tilde double one. This is acceleration, the value of acceleration, derivative of this, and the distance between equals to the gradient of V2 minus V1 and multiplied by ELOS. Line of sight. This one, we already know it. If you remember, from 0 to infinity, I can write a little bit different like this. V and M R over R 2 n plus 1 y n m theta 2 lambda 2 minus R over R1 n plus 1 y theta 1 lambda 1. So we could see that these parameters, which are related to the distance and the separation of the satellites, or is the distance between the satellites, the velocity of the change of the satellite, and this acceleration between the satellites. And this is the position vector if the difference between the satellites are connected to the potential difference between the satellites, but not the potential difference, but the gradient of multipliable line of sight. Therefore, it can be, we can right now, we can simplify this formula a little bit more with this. So we already know that the gradient operator is derivative with respect to R, ER, plus derivative with respect to theta, E theta, derivative with R sine theta, E lambda. That was it. If I apply this operator to the potential difference, it's a little bit long derivation, but I write the results here. It is in part of my book. So summation minus n spherical harmonics I1 to 2 minus 1 I m plus 1 Ri RRI m plus 1 is vector spherical harmonics of theta I lambda I plus minus I again vector spherical harmonics of type 2 Ri. So this is the formula for, and the total is multiplied by the line of sight. Yes, that's it. On one side, we have this equation. On one side, if you remember, I can write it here again. One side, we have this equation, and the result of this should be acceleration minus divided by rho bar. So this is an observation equation. What is known? The coordinates of the satellites are known. The velocity of the satellite is known, therefore its one is known. The distance between the satellite is measured. The velocity can be determined from that, and also the acceleration can be determined from that. So as you see, all parameters on the right-hand side are known. They are measurements. And the only unknown parameter will be V&M on the left-hand side. Ri is the position of geocentric distance of the satellite, and theta I and lambda I are the latitude and longitude of the satellite. So, and I is the number of satellites. You see number of satellites. So we have two satellites. So the number of satellites here. This is an observation equation. We have V and M as unknown parameters, one side, and we can create a system of equations having this unknown, this parameter as unknown, and this one as the right-hand side, which is this one as the measurement parameter. So what is important here that you know is that here the spherical harmonics are determined from the derivative. Actually, do you see derivative of a spherical harmonic are here? For example, this term is the radial derivative, and when it involved with this vector spherical harmonics again, these are horizontal derivatives, or in other words, derivative with respect to theta and lambda. So as you see, the derivative of the spherical harmonics are used here, not the spherical harmonics themselves. So